So we're going to start with this same question that we had before, but instead of having the amount of liquid coming in being the same as the amount of liquid going out, let's change it to not being leaving at the same rate, but the well-stirred mixture, how about we have it leave at, it's going in at 20 litres per second, so 10 litres per second. Just so that we've got a different rate going in and out. All right, so I need to change that up on here. Stuff is coming out of there at 10 litres per second. But all the other details from this question are the same. So what were the details? Well, the tank originally has 10,000 litres of brine, which is salt water, and the concentration originally was 1 kilo per 100 litres. Then we got some brine, which was 2 kilograms per 100 litres, and started tipping it in at 20 litres per second. But now we're also at the same time removing 10 litres per second of the solution. So the question then will be, get an equation for the amount of salt in there over time, at any particular time. And the way we arrive at our answer is to look at the rate of change of the amount of salt. If we know that the rate at which the amount of salt in the solution is changing, then we can solve that differential equation to figure out what the amount of actual salt is in there. And this is important. We said before, the Q dt, the rate at which the quantity is changing, now Q can be the actual amount of salt in kilograms, the rate at which that's changing is the rate of the salt entering minus the rate of the salt leaving. So that's where we're going to pick up now and do our answer. So we need to write down that dq dt now the rate of salt entering. All right, we've got 20 litres per second of a 2 kilogram per 100 litres solution. So that's the rate at which salt is coming in. We have 20 litres per second of this 2 kilogram per 100 litre solution, minus the rate at which we're going out. Now, we're going out at 10 litres per second times, and now we need to know the concentration of the salt that's going out. Well, we don't know how much because it keeps changing. That's the thing. But we know that the amount of salt in the system at any particular time is Q, which is some function of T, right? Q is some function of T. So I'm going to say we've got an amount of salt in there, Q kilograms at whatever time T, and that's how much is in there. So its concentration is the amount in the volume of liquid. What volume of liquid do we have? Well, we've got our 10,000 litres, but that's what the volume was at the start. Now the volume's going to be changing. Well, there's 20 litres coming in and there's 10 litres going out. So it's obviously getting more and more volume in there. How much more? Well, 10 litres every second, right? 10 litres extra is going in there every second. So we've got 10,000 plus 10 litres every second. So I'm just going to say for each time unit T, where T is in seconds, we're going to have that much more volume of liquid in there. So after 1 second, there'll be 10 litres more in there. After 2 seconds, there'll be 20 litres, 10 times 2 more. So it'll be 10,020 after 2 seconds. So that sorts out the volume. Q keeps changing, but that's the amount of salt that's in there. So there's our equation written out with the amount going in, or the rate of salt entering minus the rate of salt leaving is our rate of change of our amount of salt. And then, of course, I just go, well, we've got litres there and we've got litres there. So they cancel. And I have 20 times 2 on 100. 40 on 100 is 0.4. So I've got 0.4 kilograms per second minus. Now, I guess I've done not a favour here. What is this in? Well, that's Q kilograms. And this at the bottom is how many litres we have. So I really should have written that in before if I'm going to be using this idea. So the litres cancel and we end up here with 10Q on 10,000 plus 10T kilograms per second. So that's 0.4 minus 10Q, well, let's divide by 10, minus Q on 1,000 plus T. And of course, that's all in whatever that is, it's kilograms per second, but I'm not so much worried about the kilograms per second. This is my dq dt, which I'm interested in because I'm now going to want to solve that differential equation to figure out what is the equation for the actual amount of salt in there at any time t. So I'll go over here, get myself a bit of space and solve that. So I'm solving dq dt equals 0.4 minus q on 1,000 plus t. I'm solving that differential equation there. So what I might do is put it all in as one fraction, but first I'll just make sure I've got enough room. So hold on a tick. Okay, I can see I've got enough room. I was thinking this one's going to take quite a bit of effort because this is beyond the scope of the New South Wales syllabus that I'm actually going to have to use an integration factor here because it's not separable, right? You need to be able to separate the variables in the New South Wales syllabus. So what they would have to do is if they're going to ask this question, earlier on, they would have to actually give you the integral and just ask you to show that the integral satisfies that differential equation. For example, they would have to say something like, show that Q equals 400 T plus 0.2 T squared plus 100,000 on the integration factor. They would have to say, show that that satisfies the differential equation dq dt equals 0.4 minus q on 1,000 plus t. Because we can't actually do the integration required in our course. It's not that hard, but it's extra material that's not in the course to do. So that might be their first part. They might have the same question as I've just explained with 20 litres of the 2 kilogram per 100 litres going in and 10 litres per second coming out. But they would have to start by saying, look, first of all, show that answer there satisfies that differential equation. So you might show it. And then when you come to here, you'd go, in part one, I've shown that the derivative of this is this. So, bar the constant being the correct constant, we're going to assume that this is the correct answer to that question. So that's the correct differential equation. But I'm just going to tell you straight on up that there is the answer to that differential equation in this situation where I've evaluated the constant already. So perhaps a typical question that they might ask if they're not going to put it this way, they don't want to have a number out here. So what they might do is they might have water entering the system that has no salt in it, and that would solve that problem. You know, you could still have a certain amount of water being poured in the system, diluting it, but no actual salt entering the system, and then you could have this more sort of difficult situation, but yet something you could still separate the variables.